So lesson 3 in our syllabus is for the dot product of vectors. Vectors in the plane or vector in three-dimensional space. And there's a simple geometrical definition of the dot product. If you take vectors u and v, the dot product is the product of their lengths or their magnitudes times the cosine of theta, where theta is the angle between the two vectors. And it doesn't matter whether you take theta going in the positive or counterclockwise direction, or in the negative or clockwise direction. In one case, you get theta, in the other case, you get minus theta. But the cosine is what is called an even function. Cosine theta equals cosine minus theta. So it doesn't matter which direction you take. And this is the dot product of two vectors. So, for example, if two vectors are perpendicular, that means the angle between them is pi over 2 radians. No matter what the lengths of the vectors, the dot product is the product of the lengths and the cosine of the angle, but the angle is pi over 2, and cosine of pi over 2 is 0. So if two vectors are perpendicular, their dot product is 0. And conversely, if you take two non-zero vectors, so the lengths are positive, if the dot product is 0, that means the cosine of theta is 0. And that only happens when theta is plus or minus pi over 2 radians, which means the vectors are perpendicular. So the dot product gives us a way to determine the perpendicularity of two vectors. Two vectors are perpendicular if and only if the dot product is 0. If you have two vectors pointing in the same direction, say u and v, the angle between them is 0, and the cosine of 0 is 1. So when you take the dot product, you get the product of the lengths times the cosine of 0, which is just 1, so it's just the product of the lengths. On the other hand, this is the other extreme case. If you take two vectors in exactly opposite directions, so here's the vector u, here is the vector v, and the angle between them is pi radians, then when you take the dot product, it's the product of the lengths times cosine pi, which is minus 1. So in this case, the dot product is the negative product of the lengths. This also shows you that a dot product can be positive or negative or 0. If you take, for example, two vectors in the plane, this is the origin. The first vector just goes to 1, 0. Make this a little bit neater.
Professor,
Yes.
how do you get theta is equal to pi over 4 radian?
How do I get, that's what I'm explaining. If I
Okay.
take the vector u as 1, 0, and the vector v, which is 1, 1, right? The angle, this is a right triangle. This is length 1, this is length 1, so it's an isosceles right triangle. So that means the two acute angles are both pi over 4. Right? It's a right triangle, but it's isosceles. These two sides are the same length. So these two angles are equal, and they add up to pi over 2 because it's a right triangle. And if they're equal and they add up to pi over 2, each of them is pi over 4. So theta has to be pi over 4 radians. What are the lengths of the vectors? The length of the vector u, the coordinates are 1, 0. So the length of u is, you take the square root of the sum of the squares of the coordinates. 1 squared plus 0 squared is 1, and the square root of 1 is 1. For the vector v, the length of v is square root of 1 squared plus 1 squared, which is the square root of 2. And the angle pi over 4 has cosine equal to 1 over the square root of 2. So if I take the dot product of u and v, the u has length 1, v has length root 2, cosine of pi over 4 is 1 over root 2. The root 2's cancel, and you just get 1. So that is, so that's some examples of calculating some dot products. Now, there is a very nice formula for the dot product in terms of the coordinates. So let me see if I can turn the page here. So suppose we have two vectors in the plane or in three-dimensional space. It doesn't matter at all. So here's one vector. Let's say this is u with coordinates u1, u2, u3. You'll notice in the book, vectors are always written in boldface, but I don't have a way to write boldface on a piece of paper. So I just put this sort of arrow over the letter to indicate that that's a vector. So here's the vector u, and here's the vector v, and its coordinates are v1, v2, v3. So we know that the dot product of these two vectors is the length of u times the length of v times the cosine of the angle between them. But you also have learned.
Professor, can you go down a little bit?
Sure.
Thank you.
So this is u, this is v, this is the dot product. But you also know from trigonometry or from geometry what is called the law of cosines. So the law of cosine says the following. If you have a triangle, let's say this is A, this is B, this is C, and this angle between A and B is theta, then the law of cosine says that C squared, this side opposite the angle, is A squared plus B squared minus 2AB times the cosine of this angle. Right? So that's the law of cosines. If this were a right triangle and this angle is theta, then cosine theta is 0, and this is just the Pythagorean theorem. A squared plus B squared equals C squared. So the law of cosines is a generalization of the Pythagorean theorem. So if we look at this triangle, this is the vector u. This is the vector v. This is the vector u minus v. So we have a triangle where the length of this side is the length of u, which is the square root of u1 squared plus u2 squared plus u3 squared. This side is the length of v, which is the square root of v1 squared plus v2 squared plus v3 squared. And the law of cosines applied to this triangle says that the length of u minus v squared is equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times the cosine of the angle between them. But this is exactly, uv cosine theta, that's exactly the dot product of u and v. So I can write this as u squared plus v squared minus 2 times the dot product of the vectors u and v. If I rearrange this, this says that 2 times the dot product of u and v. Let me write this as dot product. This is the dot product of u and v. So 2 times the dot product of u and v is equal to the length of u squared plus the length of v squared minus the length of u minus v squared. The length of u squared is u1 squared plus u2 squared plus u3 squared. The length of v squared is v1 squared plus v2 squared plus v3 squared. What's the length of u minus v? U minus v, when I subtract these two vectors, this is the vector whose coordinates are u1 minus v1, u2 minus v2, u3 minus v3. So when I take minus the sum of the squares of the coordinates, so I'm subtracting minus u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. So now you have to do a little bit of high school algebra. I have 2 times the dot product of u and v is this plus this minus this. So I have u1 squared plus u2 squared plus u3 squared plus v1 squared plus v2 squared plus v3 squared minus this expression squared. When I square u1 minus v1, I get u1 squared minus 2u1 v1 plus v1 squared. When I square u2 minus v2, I get u2 squared minus 2u2 v2 plus v2 squared. And when I square u3 minus v3, I get u3 squared minus 2u3 v3 plus v3 squared. And if I look at this, I see there's a lot of cancellation. Here's u1 squared, here's minus u1 squared, they cancel. u2 squared minus u2 squared, they cancel. u3 squared minus u3 squared, they cancel. Similarly, v1 squared cancels v1 squared, v2 squared cancels v2 squared, v3 squared cancels v3 squared. So all I'm left with on the right-hand side is minus 2u1 v1, so that's 2u1 v1, minus is plus 2 u2 v2, minus, they cancel, so that's plus 2 u3 v3. So 2 times the inner product is 2 times this. If I cancel the 2's, I just get a formula for the inner product of u and, or the dot product. The dot product is also called the inner product. And the dot product of u and v is the product of the coordinates pairwise and add them up. It's the sum of the pairwise product of coordinates. u1 v1, u2 v2, u3 v3. So if you're given 2 vectors, this is almost always the way you calculate their dot product. So let me just write that formula down again. If u is u1, u2, u3, and v is v1, v2, v3, then the dot product of u and v is u1, v1, u2, v2, u3, v3. And if you were just in the plane in 2 dimensions, if u is u1, u2, and v is v1, v2, again, the dot product of u and v, you only have 2 pairs of coordinates, so it's u1, v1 plus u2, v2. So for example, if u is the vector 1, 0, and v is the vector 1, 1, then the dot product is 1 times 1 plus 0 times 1, which is 1. If u is the vector 6, 7, minus 3, and v is the vector 2, minus 9, 11, what's the dot product? If you had to calculate this by computing the lengths of the vectors and trying to figure out the angle between them, that'd be very hard. But our simple formula now makes it easy. U dot V, the dot product, you take the products of the first coordinates, 6 times 2, plus the products of the second coordinates, 7 times minus 9, plus the products of the third coordinates, minus 3 times 11. So I get 12 minus 63 minus 33, which is minus 41 minus 33 is minus 74, I think. So that's the answer, minus 74. Let me make another remark. A unit vector is a vector whose length is 1. So for example, the vector I, which is 1, 0, has length 1, because the length of I is square root of 1 squared plus 0 squared. If I take the vector U with coordinates 3/5 minus 4/5, the length of U is the square root of 3/5 squared plus minus 4/5 squared. That's the square root of 9 over 25 plus 16 over 25. That's the square root of 25 over 25, which is the square root of 1, which is 1. So this is also a unit vector. Suppose I take the vector V, whose coordinates are 3 minus 4. So the length of V is the square root of 3 squared plus minus 4 squared, which is the square root of 25, which is 5. So this is not a unit vector. But if I take the vector V and I multiply it by its length, reciprocal of its length, or I divide by its length. So 1/5 times V, when you multiply a vector by a scalar, you multiply each coordinate by the scalar. So I get back this vector. So the length of 1/5 V is 1. And this is a general fact. If the length of a vector V is some number C, which is positive, it's not the 0 vector.
Wait, Professor, can you go over really quick, the other page, just to take a picture really quickly?
Yeah, sure. So again, I'm going to post this on YouTube so you can see the whole thing, but you can certainly do a screenshot if you like.
Okay, thank you. I got it.
So if you take any non-zero vector, so its length is some positive number C, then if I take the vector 1 over C, this is just a positive number, times the vector V, the length of a scalar times a vector is just the absolute value of the scalar times the length of the vector. C is positive, so this is 1 over C. The length of the vector V is C, and 1 over C times C is 1. So if you take any vector and divide by its length, you get a unit vector. Or in other words, if I take any vector V different from 0, then V divided by its length is always a unit vector. It's length 1. Right? So if you think about it sort of geometrically, that's maybe kind of clear. And one thing that's always very useful to know, and this comes up a lot in physics, for example, you have a vector u and a vector, let's call this vector v, and a vector u. And you can think of it like this. Suppose you drop the perpendicular. These are vectors emanating from the origin. If you drop the perpendicular line segment from u to v, then this vector that I'm making very dark, this is sort of like the shadow of u on v, or the projection of u on v. So this vector is what we call the projection. PROJ stands for projection
Hello,
of the vector u in the direction of the vector v.
hello.
Right?
Oh yeah. Hello, school. Any class, Luna?
Your mic is on.
Yeah, okay. All right. No.
Right? So here's u, here's v, and this is the projection of u onto the vector v. And there's a nice formula for this in terms of the dot product. And the formula says that the projection of a vector u on a vector v is let's see, let me see how I could describe this geometrically. Suppose the angle between them is theta. So the dot product of u and v would be the length of u times the length of v times the cosine of theta. And if I divide, so I want to make sure u and v are non-zero vectors. So v is not zero. So the length of v is positive. So if I take the dot product of u, if I take v divided by its length, I'm just dividing this equation through by the length of v. This is the length of u times the cosine of theta. And this is a unit vector, because I have the vector v divided by its length. This is a unit vector in the direction of v. Now, if you think of this as a right triangle, here I have an angle theta. The length of this vector divided by the length of u is the cosine of theta, right? The definition of theta in a right triangle is the adjacent side over the hypotenuse. So in this triangle, the cosine of theta is the length of the projection of u in the direction v divided by the length of u, right? That's just the definition of the cosine. You have a right triangle, the cosine of an acute angle theta is the length of the adjacent side divided by the length of the hypotenuse. This is the hypotenuse, the length of u. This adjacent side is the projection that we're interested in. So this says that the length of the projection of u in the direction v is equal to the length of u times the cosine of theta. This is exactly the same as the dot product suppose I multiply this by 1. Another way to write this as 1 is the length of v divided by the length of v times the length of u times the cosine theta. And now what's in the numerator is the dot product of u and v divided by the length of v. So the length, the magnitude of the projection of u is the dot product of u and this unit vector in the direction of v. So the projection of u in the direction of v, it's a vector of this length, u dot v over the length of v, and it's in the direction of the vector v. A unit vector in that direction is the vector v divided by the length of v. And the length of v times the length of v is the inner product, the dot product of v with itself, times the vector v. So, so this is a very precise and correct derivation of the formula for the projection of u on v. Though the important thing in this course is just to be able to know and be able to use the formula. So let me just write this down again. So I have two vectors, u and v. And I have the projection of u in the direction of v. And this is the vector. It's in the direction of v, so it's going to be some scalar multiple of the vector v. And the coefficient is the dot product of u and v divided by the dot product of v with itself, which is the length of v squared. So for example, if u is the vector 4, 1, and v is the vector 3, 4, so I'll draw a picture of these. So the vector 4, 1 is there. And the vector 3, 4 is there. And if we want the projection of u onto v, so here's u, I'm going to take this perpendicular. So this vector in red is the projection of u in the direction of v. So our formula says this is u dot v over v dot v times the vector v. The dot product of these two vectors is 3 times 4 plus 4 times 1 over the length of v squared, which is the dot product of v with itself, 3 times 3 plus 4 times 4, times the vector v, which is 3, 4. So this is 12 plus 4, this is 16, over 9 plus 16, and 9 over 25, times 3, 4.
Professor,
Yes.
do you start with u or v? Because the formula is vector u dot vector v. But here you have 3, 4 plus 4, 1. Do you start with vector U or vector V? Right.
So again, the letters don't matter. They could be X, Y, Z, or W. But the formula is if you take the projection of U in the direction of V, this is equal to the dot product of U and V divided by the dot product of V with itself times, that's a scalar, times the vector V. So if U is 4, 1 and V is 3, 4, the dot product is 16.
Yeah, Professor, my question is U is 4, 1, right?
Yes,
But you put 3, 4 here. And the formula is U vector U dot vector V.
no. So U is 4, 1 and V is 3, 4. So
Yeah.
what is the dot product of 4, 1 and 3, 4? It's 4 times 3
Sure.
plus 1 times 4,
Mhm.
or it's the same as 3 times 4 plus 4 times 1. It doesn't matter. In
Oh,
both
okay.
cases, it's 12 plus 4 is 16.
So it can be that way, right? Okay.
Yeah, I mean
Okay.
numbers. 3, 4 is the same as 4, 3. Right? The dot product of V with itself is 25, and the vector V is
3, 4.
3, 4.
Okay.
So the projection of U in the direction of V, it's 16 over 25 times the
Yeah.
vector 3, 4. Okay. Now, there is another product of vectors that is possible in three-dimensional space. And that is what is called the cross product. So let's see, this is page 5, page 6.
So 3 dimension is cross product.
Right, that is, there's no cross product defined for vectors in two-dimensional space. We're
Okay.
only working for vectors in three-dimensional space.
Okay.
So this is really section 1.4, 13.4, I think. So this is the cross product of vectors in three-dimensional space, in three space. And when you have a vector, it has a length and it has a direction.
Yes.
So let me. So we have vectors U and V, and I wanted to find the cross product. So instead of a dot, I use an X here. So this is a vector, and to describe the vector, I have to give its length and I have to give its direction. Its length is the length of U times the length of V times the sine of the angle between them. So here's U, here's V in three space. Here's the angle between them, because two vectors, no matter how they are in three space, define a plane. So there's an angle between them. And the magnitude of this vector is the product of the lengths of the vectors times the sine of the angle between them, not the cosine. And we take this angle theta always to be between 0 and pi. And
Professor,
yes,
can you explain that? You said the angle between them?
well, we have vectors U and V.
Uh-huh.
So two vectors, two lines in space determine a plane.
Okay.
So these two vectors lie in the same plane and there's an angle between them.
Okay.
Right? That angle we call it. It's just like with the dot product. We had two vectors and there was an angle between them. The dot product was a scalar equal to length of U, length of V times the cosine. The cross product is not going to be a scalar, it's going to be a vector. but it does have a length, and this is the length. And the direction of this vector is obtained from or determined by a right-hand rule. So it's going to be a vector perpendicular to both u and v. And if you think of two vectors, there are two perpendiculars to those vectors, right? If you take this plane, there's a perpendicular through this origin. And you have to determine which is the plus and which is the minus direction. So the positive direction is going to be determined by the right-hand rule. It means you take your right hand, you place it so u is your fingers are in the direction of u. You rotate it to v through an angle of no more than pi, and your thumb is pointing in the positive direction. So in this case, the way I've drawn it, the cross product is a vector which is pointing down from the plane of my piece of paper. Okay. So that is a kind of a physical description of how you determine the vector. So u cross v is always a vector perpendicular to both u and v. So this is really very easy to visualize because you live in three-dimensional space. It's not like we're working in 4 or 5 or 500 dimensions. This is just 3 space. It's the space you walk around in. If you have a plane and you take 2 vectors in the plane and you rotate one into the other using your right hand, your thumb is pointing in what is going to be the positive direction with respect to that. And if you rotate v into u instead of u into v, you'll see your thumb is pointing in the opposite direction. If 2 vectors are parallel, so the sine of the angle between them is 0, then the cross product is 0 and it doesn't have a direction because the 0 vector doesn't have a direction. But this is it. This is the definition of the cross product of vectors. And let's try to look at an example. It's always hard to draw vectors in 3-dimensional space. Suppose I take the vector, I'm going to pick an example that's in the book where there's a picture on page 838. So I take the vector u to be 1, 1, 0. So if this is the x, y, z space, so this is x, y, and z. The vector 1, 1, 0 is here. It's in the xy plane. So this is u, which is 1, 1, 0. So as I take v, would be the vector 1, 1, square root of 2. So that's a vector which is sitting directly over this vector in space. So this is my vector v, whose coordinates are 1, 1, square root of 2. This is my vector u, whose coordinates are 1, 1, 0. Now, the length of u is the square root of 1 squared plus 1 squared plus 0 squared, which is the square root of 2. The length of v is the square root of 1 squared plus 1 squared plus the square root of 2 squared, which is 1 plus 1 is 2 plus 2 is 4, is the square root of 4, which is 2. So this vector has length 2, and this vector has length 1. And what is the angle between them? if we were to look at the plane cutting through these two vectors, it's like here we've gone square root of 2 units in this direction, and we're directly above that at height 2, right? This vector has length 2. This vector has length square root of 2. And what is this? 4, 2. This is also square root of 2. So this is also going to be an angle pi over 4. So the magnitude of the cross product, or the vector product, is going to be the length of the vectors times the sine pi over 4. That's root 2 times 1 over root 2, so it's 2. So this cross product has a magnitude or length, which is 2 units. Right? And the direction of u and v, I don't even know how I would do that. It's like, I take u and I rotate it into v, and the direction my thumb is pointing is the direction of the cross product. Right? So it's a vector perpendicular to this plane and going in that direction. Again, the important thing is to know the definition of the cross product, and this is it. Now, how do we calculate these things? That's actually very interesting. If you know the coordinates of u and v, how do you calculate the cross product? And we do that as follows. Let's look at one more special case. Suppose we're in 3-dimensional space. So we have unit vectors in the x, y, and z directions, which are I, j, and k. So I has coordinates 1, 0, 0. J has coordinates 0, 1, 0. And k has coordinates 0, 0, 1. So each of these is a unit vector. The length of I, the length of j, the length of k, these are all equal to 1. So if I take the cross product of the vectors I and j, that's going to have length. So, and the angle between any two of these vectors is pi over 2. So for any two of these vectors, the angle between them, theta, is pi over 2. And the sine of pi over 2 is 1. So I cross j, I cross k. Anyway, this is I cross j, j cross k, and k cross I. These all have length 1, because it's the product of the lengths times the sine. You get 1 times 1 times 1. So all three of these cross products have length 1. Question is, what direction do they point in? So if you take I and rotate it into j, your thumb is pointing up. So it's in the direction of the positive z-axis. So I cross j is equal to k. If I take j and rotate it into k, my thumb is pointing in the positive x direction. So j cross k is equal to I. If I take k cross I, if I rotate k into I, my thumb is pointing in the positive y direction. So k cross I is equal to j. So we have these basic formulas. I should also say one other thing. U cross V, and V cross U, the formulas for the magnitudes are the same. They have the same length. But if you rotate U into V, you're pointing in the opposite direction of when you rotate V into U. So U times V is minus V times U. So when you do the cross product of vectors, the order matters. Now there is a formula for computing the cross product in terms of the coordinates. And let me just write that down now. So that's really all you're going to need for working homework problems, I think. So suppose we have a vector u, which coordinates u1, u2, u3. And v has coordinates v1, v2, v3. So you can compute the cross product u cross v as follows. It's one way to remember this. If you don't know what a 3x3 determinant is, it doesn't matter. So, but one way to remember it is to write a 3x3 determinant where the second row are the coordinates of u, the third row are the coordinates of v, and the first row are I, j, k. And if you use the standard rule for evaluating a determinant, you get this is equal to u2 v3 minus u3 v2 times I minus u1 v3 minus u3 v1 times j plus u1 v2 minus u2 v1 times k. And in terms of coordinates, this is the cross product. So for example, if U had coordinates 2, 3, 4, and V had coordinates 3, 2, 0, U cross V is going to be equal to what vector? It's going to be, let me write it, this is the easy way for me to remember it. IJK 2, 3, 4, 3, 2, 0. So this is going to be minus 8I minus 12 plus 12J plus 4 minus 9 minus 5K. So if you go back and check this formula, or you apply this formula with these numbers, U1, U2, U3, V1, V2, V3, this is what you get. And in this course, since you have the book at hand at all time, you don't have to memorize the formula, but it's good. But this is an easy way to remember it. But you can always just look up the formula, and when you have to solve a problem, you solve a problem. I should make one other remark about the geometrical meaning of at least the length of the cross product. So suppose I have a vector u and a vector v, and this is the angle between them. So the length of the cross product is the length of u, the length of v, times the sine of the angle between them. Suppose I make a parallelogram whose sides are u and v. So what is the area of the parallelogram? It's the base times the height. So let's say this is the base, u has length, magnitude of u. This is the height. If the length of this vector is v, this height is exactly length of v sine of theta, right? The sine of theta is this over this. So this is the length of v times the sine of theta. So what I have is the length of u times v sine theta. That's equal to the area of the parallelogram. So if you want a way to understand the cross product geometrically, it is exactly this. The length of the cross product gives you the area of the parallelogram. If you want to find the area of the triangle formed by the vectors u and v, so the area of the triangle is half the area of the corresponding parallelogram. So that's 1/2 the length of the vector u times v. Okay, that's enough for today. If you have questions, I will be back online tomorrow for vector calculus at 11 o'clock.